If a polar equation passes a symmetry test, then the graph will exhibit that particular type of symmetry. If you remember symmetry, for every point you have on one side of the line or point, then you'll have a matching point on the other side, and you can get multiple points from the same amount of work. By contrast, and this, notice I've underlined this, if a polar equation fails a symmetry test, the graph may still have that type of symmetry. So the graph of a polar equation may have a symmetry even if it fails a test for that particular type. Nevertheless, the symmetry tests are useful because if we can find symmetry, we can use that to draw our graph using fewer points. For every point we derive, we can get 2 for the amount of work. Quick review of the types of symmetry. A graph is symmetric with respect to a line if you reflect over the line and leaves the graph unchanged. This line is called an axis of symmetry. Symmetry about the origin. This is when we were graphing by transformations in both Algebra 2 and Trig. And in this course, for that matter, we never really talked about origin symmetry. Graphing over the origin or origin symmetry is for every point xy, there's a point negative x, negative y. So if I knew that 3, 5 was on my graph, then negative 3, negative 5 would also be on my graph. So when I do the test for symmetry, I can get 1 point, say it passes symmetry, and then I have multiple points. Test for symmetry in polar coordinates. We're going to test for 3 types of symmetry. Let me put an arrow in here. I think it works a little better. So our first type of symmetry is going to be symmetry with respect to the polar axis. Again, the polar axis would be the positive x-axis if we were graphing in the coordinate plane. In order to test for that type of symmetry, polar axis or x-axis symmetry, we will replace theta with negative theta. And if we get the same equation back that we started with, we have symmetry with respect to the polar axis. So that if I got r theta, then I would know r negative theta would also be on the graph. Again, 2 points for the work of 1. This would be a good time to go back and review even and odd functions for the trig functions. Symmetry with respect to the line theta equals pi halves, right up the middle. That would be over the y-axis. We would have symmetry over the y-axis. For every r theta, we would get a negative r negative theta. But remember, when you get negative r, you're actually going to go the other direction. So you would actually get r negative theta as the actual point. Then again, we talked about symmetry with respect to the pole or origin. Again, we would replace r with negative r, and if an equivalent equation results, the graph would be respective or symmetric with respect to the pole. We would get, for every r theta, we would get a negative r theta going out the other direction. If a polar equation passes a symmetry test, then we know it has that type of symmetry. However, if it does not, it may still have the symmetry. All right, so I'm going to set up a table of values. I'm not going to take time to put in a unit circle and look up the cosine of each of our angles. I've set up our angles. Again, I put in the angles 0, pi over 6, and so forth, all the way up to pi. We've seen that we begin to repeat after that point. The blue bar is simply covering up those values. So I looked up the cosine of each of these angles and then did 1 minus that cosine and rounded off to an applicable value. And I got 0, 0.13, 0.5, 1, 1.5, 1.87, and 2. Now to check for symmetry, let's go back a page or 2. If I want to check with symmetry with respect to the polar axis, I will replace theta with negative theta and see what happens. If I get back the same equation I started with, then I will have that. Bring up my document camera, and again, I will apologize for the quality of the video on the document camera. The equation was R equals 1 minus cosine theta. Now, if I replace theta with negative theta, I'll have R equals 1 minus cosine of negative theta. If you'll remember your trigonometry, net theta and negative theta would have the same cosine. Cosine is x. So the cosine of negative theta is the same as the cosine of positive theta. So I would get R equals 1 minus cosine theta. So that tells me that our graph passes symmetry for the polar axis. So for every point I get above the polar axis, I'm going to get a matching point below. Hence the reason I only had to go from 0 to pi, because every point I find in the top, I can find the matching point in the bottom. Going back, next, let's check for symmetry over the y-axis. Again, we would replace r theta with negative r theta and see if we get the same equation. So if negative r equals 1 minus cosine, oops, I forgot to bring the document camera up in focus where you can see it. So I have 1 minus cosine theta. I will replace that with negative r equals 1 minus cosine negative theta. Now we know the cosine of negative theta is just the same as the cosine of positive theta. In this case, the two equations are not the same, and we have failed the test for symmetry over the origin, however, or pole. However, that doesn't mean our graph doesn't have that type of symmetry. It just means it didn't pass that particular test. Going back to our third type of symmetry, quick review. That was respect over the y-axis actually. Symmetry with respect to the pole or origin, we will replace the r with negative r. So in the first one, we replace theta with negative theta. In the second, we replace both. In the third, we replace the r. So our equation was 1 minus, or r equals 1 minus cosine theta. If I replace r with negative r, 1 minus cosine theta, I don't have that type of symmetry either. The equations did not come out the same. So our graph passed for symmetry over the polar axis, but it did not pass symmetry for the other two types over the pole or the y-axis. We plugged in our values, and for every point we get above, we'll get a point below. So let me put in a few points very quickly. Okay, something weird is happening with my computer, if you'll bear with me. Okay, now that I've fixed my computer issues, I have some points ready to plot. We had 0, 0 at the pole. We had pi over 6 at 1.3 or 0.13. Now it's very difficult to plot it in. I'm going to go to the next page. I know I don't have it already graphed. Okay. Anyway, At pi thirds, we're about a half a square out. You can see we're getting a circle simply. At pi halves, we're at 1. 2 pi thirds, we're at 1.5. And I won't finish plotting all the points because the graph really isn't big enough to fit on the screen. And if I had the smart board at school, I could get a much bigger graph. All right, back to the lesson. I stopped for a few moments and put it on pause while I went to my book online and copied a picture of the particular graph. These are the ordered pairs we plot, and here are all the points plotted in. However, if you will remember, we had found that our graph had symmetry over the polar axis, or the x-axis, that is where the coordinate plane, and all of these points above would repeat. So let me see if I can put the graph of the completed graph. Bring that to the front and put it on top. We simply took all the points from the top, repeated them in the bottom. You'll notice you get that kind of a heart shape that has a name, which we'll discuss in a few moments. All right, graphing a polar equation with r equals 1 plus 2 sine theta. You'll notice a similarity between the two equations. We have 1 minus cosine theta. This time we have 1 plus 2 sine theta. So a number and a coefficient, I guess, if you please. All right, back to example 3. We're graphing r equals 1 plus 2 sine theta. If we check for symmetry, if we replace theta with negative theta, if you'll recall, theta was odd, sine of negative theta would be the opposite of the sine, so this would become 1 minus 2 sine theta, and it would not have polar axis symmetry. If we replace r and theta with a negative, check for a line over the y-axis, now we get negative r and negative 2 sine theta, and again, it fails the test. If I replace only the r, again, it failed all tests for symmetry. However, it doesn't mean it doesn't have the symmetry, it just means it didn't pass the particular test. So we can't use symmetry for graph. I've gone ahead and for the respect to the video, replaced all of our values and drawn out our graph. I have taken values for theta from 0 to 5 pi over 6, the top half of the circle, plotted the points. Then I plotted points from 7 pi over 6, 4 pi, 3 pi halves. So I did the first 2 quadrants here. Third quadrant, you'll notice we curled up here. And then in the fourth quadrant, we've gone back through the polar axis, or pole, one more time. And you'll notice we got a very similar shape to what we had before, but with before we were over the y-axis, now we're kind of centered on the x-axis, or polar axis. So, although our polar equation failed the test for symmetry, if we go back and look at it, you can see that it is still symmetrical about the y-axis. So it does have y-axis symmetry, even though it failed that type test. Those particular shapes are called a limousin. Limousin is French for snail. Somebody thinks the shape looks like a snail, that little dimple type shape. Depending on the values of A and B, you'll get more or less inflection, I guess would be a good word to describe it. This would be a good time for me to stop here and talk about what I expect in the course versus what's in the book. I am not going to ask you to graph the ones that are the limousin only to understand the concept. You will have to understand the previous ones that gave us the circles, however. The rest of the lesson, I'll go a little more quickly. If I were graphing r equals 4 sine 2 theta, I would get a graph that looks something like that. That's called a rosette for obvious reasons. It looks
like a flower petal. The number of petals will be defined by the number, and how far out your value of R will be defined by your coefficient, and the coefficient of theta will define how many petals you get. All right, so these are called rose curves, or some people say rosettes. Uh, Again, I'm not asking you to do all this, but I would like to expose you. If the number is an even number, we will get an even number of petals. If it's odd, we'll get an odd number of petals. You'll notice we had 2 for the number, 4 petals. We had 3, so it's odd, we got 3. So when the number is odd, we'll get that many petals. If the number is even, we will get double the petals. So 2, we had 4 petals, 4, we had 8. So you can graph these on a regular graphing calculator. Let me bring my calculator up. And when you go to mode, you want to switch to from radian. You want to make sure you're in radian degree to graph these. It won't work for some reason in degrees. And on the next line down, you would want to switch over to POL, P-O-L, for polar, because you're graphing polars. And then when you go y equals, instead of it saying y equals, it will say r equals. So if I were to graph, say, for example, 2 sine x, and instead of x, you get theta. You notice on the key theta is there, and I can graph that. And I got that circle we showed earlier. I would have to adjust my window to see that more clearly. I'm going to reset this calculator back to functions. You also would like, you should play around with the Desmos calculator graphics. The graphics are much better. All right. Again, I'm not going to require you to be able to graph this type. These are called lemniscates. Most of the work done by this, for all of this, was done by French mathematicians, and they got the name of things. So, in summary, these are the basic summaries. You can find these charts. The ones that I'm going to ask you to do, hang on just a second. Let me get a pen or highlighter. So I'm going to ask you to know and be able to do this type. Be able to understand the circle, or do a circle, know where the center is, know where the diameter or radius, and so forth. So the diameter is A, the radius will be half of A. The center of obviously would be to go out half of A from whichever. When it's cosine, you'll be on. Now, if A is negative, you're going to go to the left. If A is positive, on the right. Same thing here. So that's what I would ask you